This is my Module 6 Mastery assignment. My first topic is solving differential equations. Differential equations are equations that have rates in them. A solution is a function that has as its derivative a given differential equation, represents the fact that an entire family of functions all have the same derivative. The process we will be using is called separate, integrate, and solve. When we separate, we algebraically manipulate the differential equation so that all the y variables are on the left and all the x variables are on the right. The next step is to integrate, and this is where you integrate both sides of the equation, and you must remember to put plus c on the right side. The last step is to solve, and this is where you use your initial condition to solve for c and also solve the final equation for y. The example is 2y squared x squared. First, we must separate the variables in this problem, and we do this by dividing both sides by the equation y squared, and then we multiply both sides by the equation dx. Now we must integrate both sides of the equation. The integral of dy over y squared comes out to negative 1 over y, and the integral of 2x squared dx comes out to 2/3 x to the third, and we must include plus c on the right side. Now we must solve for y in the equation, so we have to multiply both sides by a negative. Next, we take the reciprocal of both sides of the equation to arrive at the final solution, which is y equals 1 over negative 2/3 x to the third minus c. My second topic is Newton's law of heating and cooling. Newton's law of heating and cooling is a differential equation that shows that the rate at which an object heats or cools is in proportion to the difference between the object's temperature and the temperature of the surrounding environment. The constant of integration is the constant added when integrating. This value determines which of a family of antiderivatives is the particular solution to a differential equation. The initial value is the starting value of position or velocity. It is used to help solve for a particular solution to a given differential equation. Newton's law differential equations take the form dy over dt equals ky minus b. We must first use the process of separate, integrate, and solve. So first, we must separate the variables, and we do this by doing dy over y minus b equals k dt. Now we must integrate both sides. So we get the natural log of y minus b, that is in absolute value bars, equals kt plus c. Next, we must solve the equation for y by exponentiating both sides. We use this by using the power of e. For the fourth step, we must compose the inverses of e to the x and natural log of x on the left side, and we separate the exponent on the right side of the equation. Then we rewrite the equation without the absolute value on the y minus b by converting e to the power of c to a. A is a new constant that absorbs the sign of the absolute value. Next, we add b to both sides of the equation. This gives us the general form of our equation, which is y equals a e to the kt plus b. The example that I'm going to use is the milkshake problem. The milkshake problem is your mom agreed to buy you a milkshake and she went to the ice cream store to make the purchase. The temperature of the milkshake at the time of purchase was 28 degrees Fahrenheit. Your mom put the milkshake in the cup holder of her car so that it should be delivered to you at home. The temperature in your mom's car is kept at a constant 70 degrees Fahrenheit. Unfortunately, your mom got stuck in traffic and the milkshake began to melt. When exactly 10 minutes had passed, the milkshake had warmed to 35 degrees Fahrenheit. We need to write and solve a differential equation modeling this situation and use it to estimate the temperature of the milkshake when your mom arrived home 20 minutes after the milkshake was purchased. First, we must write the equation, which is T is equal to A e to the kt plus 70. 70 is the temperature in the car. Next, we must solve for the constant A, so we can plug in 28 for T because this is the temperature at time 0. So we do 28 equals A e to the 0 plus 70, and we solve this and get A is equal to negative 42. Now we can plug this constant back into our equation and we get T equals negative 42 e to the kt plus 70. Now we want to solve for the constant k, so we can plug in the time at 10 minutes. So we do, the time at 10 minutes is 35, so we do 35 is equal to negative 42 e to the kt plus 70. So we do 35 minus 70, and this gives us negative 35. So now we need to divide by negative 42 on both sides. So this gives us 35 over 42 is equal to e to the 10k. So now we can put a natural log in order to cancel out the e. So now we have natural log 35 over 42 is equal to 10k. So we know k is equal to 1 over 10 natural log 35 over 42, and this is also known as negative 0.018. Now that we have our two constants, we can plug them back into the equation. So the equation is now t equals negative 42, e to the 1/10 natural log 35 over 42, t plus 70. Lastly, we want to find the temperature at time 20, so we must plug 20 back into the equation for t. So we get negative 42 e to the 2 times the natural log of 35 over 42 plus 70, and this gives us the temperature at 20 minutes, which is 40.833 degrees Fahrenheit.